Good morning to all. I'll be talking about porosity from well logs today. This will give you an understanding how to calculate porosity from well log. We will first talk about porosity determination from various logs, and we'll try to see how this log should be read. We know that when a well is drilled, we need to understand the formation by using well log. So we send a sonde inside the earth through this borehole, which has a transmitter and a receiver. We try to take SP resistivity log, SP on the first track and resistivity on the second track. And we know that these are used to understand the increase in radioactivity for gamma ray log, which is taken once again on the first track. And you can see that where there is a increase in gamma ray, that is actually a shale, and a decrease in gamma ray is a oil sand or a sand which may be water bearing. Increasing resistivity is a sign of porosity presence, and increasing of porosity happens in oil sands, whereas in shale the porosity is decreasing. There are three main log types which are used for porosity determination. One is bulk density, the second is sonic, the third one is compensated neutron. These logs do not measure porosity directly. To accurately calculate porosity, the log analyst must know formation lithology and fluid inputs of sampled reservoir volume. Density log uses radioactivity source to generate gamma rays. Gamma ray collides with electrons in formation, losing energy. Detector measures intensity of backscattered gamma rays, which is related to electron density of the formation. The electron density is a measure of bulk density, which we are looking for. Now we should also know that the bulk density is dependent upon the lithology, porosity, density and saturation of fluid in pores, and saturation is a fraction of pore volume occupied by a particular fluid which is intensive in nature. Now in this diagram we can see that this is the gamma ray. The blue colored is the gamma ray, and red is the caliper which takes into account the rugosity in the borehole which need to be corrected. The density is given as the dotted black one, whereas the rho B is found out from the green curve what we can see. And we can see the scale of the rho B which varies between 2 to 3, and we can see that the rho B is increasing towards the direction of the left, where it is increasing rho B. We also need to apply some density correction to the rho B value. Now in a formation, when we have drilled a borehole, we have mud cake, which is the rho MC plus HMC. And in this diagram, we can see the source from where the emissions are happening. This is the long spacing detector in the sonde, which will measure the data. And then there are short spacing detector. So there is a source, there is a long spacing detector, and then there is a short spacing detector. Rho B is equal to rho matrix into 1 minus phi, and sum of the pore spaces is filled by fluid, which is rho f into the phi, where phi is the porosity. So rho b has two components, which has the matrix component and the fluids in the flush zone. It measures electron density of a formation, strong function of a formation bulk density, and we know that the matrix bulk density varies with lithology. In sandstone, it is 2.65 gram per cc. In limestone, it is 2.71 gram per cc. And in dolomite, it is 2.87 gram per cc. The porosity equation phi is given as rho matrix minus rho b by rho matrix minus rho f, and the fluid density equation is given as rho f is equal to rho mf x xo plus rho h into 1 minus s xo. We usually assume the fluid density rho f is between 1 and 1.1. If gas is present, the actual rho f will be less than 1.0 and the calculated porosity will be too high. Rho f mf is the mud filtrate density, which is given as gram per cc. Rho h is the hydrocarbon density, and SXO is the saturation of the flush zone in decimal. The working equation for hydrocarbon zone rho b is given as phi xo rho mf plus phi 1 minus xo into rho hc plus v shell into rho shell plus 1 minus phi minus v shell into rho matrix. Rho b is a recorded parameter, which is the bulk volume. Phi xo rho mf is the mud filtrate component. Phi 1 minus xxo rho hc is a hydrocarbon component. V shell and rho shell is the shell component, and 1 minus phi minus v shell is the matrix component. If minimal shell V shell is close to 0, if rho hydrocarbon is equal to rho mf is equal to very close to rho f, then rho b is given as phi rho f minus 1 minus phi rho matrix. So phi, which is determined from density equal to phi d, is given as rho matrix minus rho b divided by rho matrix minus rho f, where phi d is the porosity from density log, which is in fraction. Rho matrix is the density of formation matrix given in gram per centimeter cube. Rho b is equal to bulk density from log measurement, gram per centimeter cube. Rho f is the density of fluid in rock pores in gram per centimeter cube. Rho hc is density of hydrocarbons in rock pores in gram per centimeter cube. Rho mf is the density of mud filtrate in gram per centimeter cube. Rho shell is the density of shale in gram per centimeter cube. V shell is the volume of shale fraction, and XXO is the mud filtrate saturation in zone invaded by mud filtrate in fraction. So let's concentrate on rho corrected, which is between 1.95 to 2.95, and we can see that it is blue in color, which is the bulk density log. We have the resistivity log in the second track, which is in semi-log scale, and the gamma ray and SP, and also the caliper is given on the first track. The next tool which is utilized is the neutron log. Logging tool emits high energy neutrons into formation. Neutrons collide with nuclei of formation atom. Neutrons lose energy, that is the velocity, with each collision. Most energy is lost when colliding with the hydrogen atom nucleus. Neutrons are slowed sufficiently to be captured by nuclei. Capturing nuclei become excited and emit gamma rays. Neutron logs depends on type of logging tool, either gamma rays or non-captured neutrons are recorded. Log records porosity based on neutron captured by formation. If the hydrogen is in pore space, porosity is related to the ratio of the neutron emitted to those count as captured. Neutron log reports porosity calibrated assuming calcite matrix and fresh water in pores. If these assumptions are invalid, we must correct the neutron porosity value. The theoretical explanation of the equation is given as phi n, which is the recorded parameter, is equal to phi xo into phi nmf, which is the mud filtrate portion, plus phi 1 minus xo into phi NaC, where plus V shell into phi shell, which is the shell portion, and 1 minus phi minus V shell into phi NMA is the matrix portion, where phi is the true porosity of rock. Phi 1 minus x6o, phi NaC is the most important part, which is the hydrocarbon portion. A neutron corrected log is given as 0.45 to minus 0.15. So in a neutron log, as we move towards the left, we get positive neutron values. The next tool, which is of importance from a logging and porosity calculation point of view, all these three logs are on the third track, which is a linear scale. We have 4 receiver R1, R2, R3, and R4, and we have 2 transmitter, the upper transmitter and the lower transmitter in the sound. Tool usually consists of 1 sound transmitter above and 2 receivers below. Sound is generated, travels through formation. Elapsed time between sound wave at receiver 1 versus receiver 2 is dependent upon density of medium through which the sound traveled. You can see here that in a wave, there are compressional wave, there are Rayleigh waves and mud waves, which has been taught to you before when I took classes on seismic, where I talked about body waves and surface waves. This gives a common lithology versus typical matrix travel time. Sandstone has a travel time delta max in Microsoft Perfect is 55.5. Limestone, the value is 47.5. Dolomite 43.5. Anhydrite will be 50.0 and salt 66.7. The working equation for the acoustic log, which is the recorded parameter delta TL, is the travel time read from log. It is equal to phi xos delta TMF, which is the mud filtered portion, plus phi 1 minus xxo delta T AC is the hydrocarbon portion. Then we have the V shell and delta T shell, which is the shell portion, and we have 1 minus phi minus V shell into delta T matrix, which is the matrix portion. If V shell is equal to 0 and if hydrocarbon is liquid, that is delta TMF is very close to delta TF, then delta TL is equal to phi delta TF plus 1 minus phi delta T matrix, or phi S is equal to phi equal to delta TL minus delta T matrix divided by delta TF minus delta T matrix. Phi S is equal to porosity calculated from sonic log reading, which is fraction. Delta TL is the travel time reading from log microseconds per feet. Delta T matrix is the travel time in matrix microseconds per feet, and delta TF is travel time in fluid microsecond per feet. We have here the sonic travel time, which is given in black, and the value is between 40 to 140 microsecond per foot. And we have the sonic porosity here, which varies between 10 to 30%. The porosity here is 30% and the porosity here is less than 30%. The response can be rewritten as T log is equal to T matrix 1 minus phi plus Tf phi, where phi is given as T log minus T matrix divided by Tf minus T matrix. T log is the log reading in microsecond per feet. T matrix is the matrix travel time, microsecond per feet. Tf is the fluid travel time, microsecond per feet, and phi is the porosity. You can see the dt value varies between 50 to 150 microsecond per feet, and sonic log is given on the third scale. We can see that the sonic is increasing on the left and the sonic is decreasing towards the right. We can have calculations for rock porosity using an acoustic log. Here is the example which is given where we are talking about calculate the porosity for the following intervals. The measured travel times from the log are summarized in the following table. At a depth of 10,820 feet, acoustic log read travel time of 65 microseconds per foot. Calculate calculate porosity and also talk. Does this value agree with density and neutron log? Assume a matrix travel time dTm, that is delta Tm, is equal to 51.6 microsecond per foot. In addition, assume the formation is saturated with water having a delta Tf equal to 189 microsecond per feet. And you can see the example solution from sonic log, which is given between 1070 to 1090 and 900, 10700 to 10900. You can see the GRC, SPC and caliper. You can see the LDC, SNC and MLLCF. You can see here the rho C and the CNLLC. We can see here the DT value and the S phi. So the black one talks about the S phi. The factors which are responsible are unconsolidated formation, naturally fractured formation, hydrocarbon, especially gas, and rugose salt sections. Response of porosity log. The three porosity log respond differently to different matrix composition, respond differently to presence of gas or light oils, and combination of logs can imply composition of matrix, indicate the type of hydrocarbon in pores. If there is a gas effect, you should remember that density phi is too high, in neutron phi is too low, and in sonic phi is not significantly affected by gas. Open hole logging tools are the most common method of determining porosity. It's less expensive than coring and maybe less risk of sticking the tool in the hole. Coring may not be practical in unconsolidated formation or in formations with high secondary porosity, such as vugs or natural fractures. If porosity measurements are very important, both coring and logging programs may be conducted, so the log-based porosity calculation can be used to calibrate it to the core-based porosity measurements. Influence of clay minerals distribution on effective porosity. You can see the phi E and the clay minerals. So we have to be very careful when it is dispersed clay. There is clay lamination and structural clays, which is rock fragments, rip-up class, clay replaced grain. You can see the phi porosity, the clay mineral presence, and detrital quartz grain in different proportions in case of dispersed clay, relay lamination, and structural clay. From the core, we get the lithophysis. Then we take a small core plug. We try to do the 4 types. We try to understand the petrophysical data and plot phi versus permeability. We also try to do a capillary pressure understanding. We compare with gamma ray log and we can classify them as flow unit 1, 2, 3, 4, and 5. And based on the flow units, we can actually correlate between the formations. And you can see here a correlation between various well logs, which has been converted into lithophases and has been correlated from well to well. Thank you very much for attending my class on porosity determination from well log. I think we come to the end of the class and we will take a next topic which will help you in understanding logs in more detail.